And when you track a spicule in these very thin white lines, which you can probably not see very well, but if you sum all the signals along the spicule and show height versus time cost for these different kind of diagnostics, you find that in calcium, you see the upward phase. The spicules don't really seem to be coming clearly down. They kind of fade out. In magnesium, you actually see nice parabolas. You see that here too, as well. And the interesting thing is that as time goes on, you often get a fading of the cooler lines and then a very rapid increase of temperature or increase of emission at the higher temperature diagnostics. You see that here as well. And so we've done statistics on this. This is not a unique thing. This happens quite a bit. And it suggests that our data suggests that the spicules will multi-threaded and different threads reach different temperatures and often undergo very rapid heating on very short time scale, less than minutes. So those are kind of some of the observational findings that we had from IRIS and SSD data. This is not something we could have done before IRIS, since we need all that temperature coverage. And it gives you a list of observational constraints. We know that there's very high speeds. We know that they have quite great lengths. These counterparts, we know what they look like. In calcium, H-alpha, and magnesium, they look like these exclusions in the blue and red wing that don't live very long, only a couple of tens of seconds. We know that there's counterparts in the transition region, the UV lines, and we know that there's a variety of transverse wave modes associated with them, and that they undergo parabolic trajectories. And of course, we've known for a very long time that they curve the boundaries of large regions and enhanced network. And as I mentioned before, there have been an enormous number of numerical models or even analytical models for spicules. I've been guilty of one myself. And none of these models reproduce all of these new observational constraints. The observational constraints for spicules now are very different from what they were 15 years ago. We really provided much more strict constraints now with all of the new data. So that brings me to another part of the IRIS science investigation, and that's something that Mats already talked about yesterday, which is that advanced numerical simulations have always played a key role in IRIS. And the reason for that is because we're looking at all of these diagnostics, or many of these diagnostics that are formed in the chromosphere. They're optically thick, they're subject to non-local rate of non-LTE rate of transfer effects, which makes the interpretation of the data in terms of physical variables challenging. And one thing that's really helped us with that has been these high fidelity numerical models that Mats talked about already yesterday, and there are a variety of different brands. We've been focusing a lot on eFrost, and the reason for that is that eFrost has tried to include as many complex kind of physical processes as possible in the chromospheric region, which is where we're observing. There are many models that pretend to have a chromosphere, but where you go and observe, calculate synthetic observables from those chromospheres, they don't look anything like the observations. eFrost does a little better, and so that's one of the reasons we've been focusing. Well, it does a lot better in some diagnostics and does a little better in others. There are still discrepancies, and Mats talked about them yesterday. And the interesting thing with IRIS is to learn from these discrepancies, compare with the observations, and then figure out what could be missing. And that's how we came to these simulations. These are simulations by Juan Martinez Secora. They're 2.5D. And for the last 10 years, whenever we've run these models, we've been looking for type 2 spicules, for very fast spicules in these models, and we've never really found a whole lot of them. I think there's one published a whole paper, or even 2 papers about one particular spicule, because it looked like it was much faster than the typical spicules. The typical spicules in these models are very low, just a couple of megameters, and they're pretty slow. They're essentially pretty well understood. They're driven by magnetoacoustic shocks that are triggered by leakage of P modes and convective flows into the atmosphere, and they just don't really have the oomph to get very fast and cause strong heating. The interesting thing was when we looked at this model after we ambient diffusion, and I'll talk about that in a minute, we found that there were actually a lot faster spicules in here. You see one there. And so we started getting very excited because they had velocities of 50 to 100 volts per second. They reached heights of 5 to 50 megameters. And there seemed to be very vigorous heating associated with them to transition region temperatures. So we decided to investigate these more, and we did that with a simulation that has has essentially got an active region size region here. This is megameters, and has a very high resolution as well. There's all the boundary conditions, and as Moses explained, I think the main parameter here is the magnetic field, and the magnetic field was meant to mimic an active region with two large regions, one here and one there. So in terms of equations, we took the usual equations that Moses already talked about, and we changed the induction equation to include the generalized Ohm's law, which means that you have a whole term and you have the antipolar diffusion. And antipolar diffusion takes into account the fact that the chromosphere is partially ionized, and Chris Morosky already talked about this yesterday. Since it's partially ionized, you really should be doing two fluid simulations. We're working on that. That's not what this is. This is still a single fluid emission simulation, but it incorporates some of the effects from the interactions between ions and neutrals through this generalized Ohm's law, through this antipolar diffusion. What the antipolar diffusions essentially captures is that the neutrals do not experience the Lorentz force. They couple collision to the ions, but that coupling is not perfect, and that allows the neutrals to decouple from magnetic field lines and allows the field lines to diffuse through the neutral gas. And as it turns out, that plays a key role in the magical appearance of these very fast spicules in that model. This is a movie that shows, there will be a movie in a minute, that shows the temperature, the antipolar diffusion coefficient, the absolute value of the velocity, and the out-of-plane electrical current. And what you will see here is a spicule form, and the movie will play again and again. And what you see as well is that there is a strong field region here, and there's some weak field that interacts with it. And the weak fields are jostled around in the convection like they always are. The convection zone is below zero. We're just cutting off the domain. We actually have 2 more nanometers below this. And these weak fields are typically not buoyant enough, not strong enough to really emerge into the atmosphere. What happens when you switch on antipolar diffusion is that you have a region here that's relatively cold. It's in the wake of a shock wave. So it cools off, and you get very strong antipolar diffusion, and that allows these weak fields to diffuse into the atmosphere. And when they do that, they bring with them all of the tension that was introduced in the photosphere, which was high beta, so the fields have to do whatever the plasma wanted it to do. It allows to bring all of this magnetic tension that it brought with it, diffuse it into the chromosphere. Once you get to the upper chromosphere, the field is in charge. It's now low beta, and the field essentially straightens itself out, and you have a slingshot effect, and you get this very fast spicule forming right there. You get antipolar diffusion along that feature, and you also have electrical currents in and around the bottom of the spicule. So this is again shown here. What we found in this model is that through the interaction of the weak and the network Bloch fields in the photosphere, you have antipolar diffusion that allows these weak fields and the tension they carry into the chromosphere. In addition to that, the antipolar diffusion concentrates the currents. It kind of wipes the currents clean and concentrates them at the edge, which amplifies the tension. And then you get this violent release of tension above the baby as well here. Sonia already talked about this yesterday. There is an enormous amount of weak fields in the quiet sun, and also in the vicinity of the strong network fields. And so what we found in the model actually fits very well with the idea that these weak fields are continuously interacting with these strong fields, and every time they do, it's not reconnection in our model, although that happens as well. But very often it's this process of diffusing the tension into the chromosphere. One of the side effects of this is that the antipolar diffusion can lead to misalignment between magnetic field lines and thermal structures, and you can see that here. The white lines are the field lines, and by the end of this movie you see a thermal structure here, like right there, which is at an angle with the magnetic field lines. This happens not everywhere, but if it happens, it will happen in the upper chromosphere where the antipolar diffusion is significant, And it could, in principle, also impact people who use the intensity structures in the chromosphere to constrain magnetic field extrapolations, for example. I think Jaime also has a result a couple of years ago where he found discrepancies between the direction of the field of the chromosphere and the direction of the fiber structures. So the model also predicts something else. It predicts that when you release this magnetic tension, it will generate transverse magnetic waves with periods that are very similar to those observed. What you see here is the out-of-plane velocity component, and it's scaled 40 plus or minus 40 kilometers per second. And so this very rapid pulse, and it rings a little bit later too. So it's very similar to, in terms of periods, what Jota Nakamoto and I found a couple of years ago when we looked at specules, and a variety of other authors that have looked at this too. And I think the next speaker can also talk about these high frequency waves. So they are naturally generated in this model, which is always nice too. Of course, it's a 2.5D model, so we can't really say much about the variety of waveforms that are being generated. Now, another aspect of this is that we find that, I've already alluded to this, that as the spicule forms, there's also heating. So what you're seeing here now is the temperature, moving as usual, and we're essentially tracking, again, in this region here, as a function of height and time, so it's a height space-time plot, the temperature, the velocity, the density, and the undergoing heating. And as you can see here, the temperature undergoes a very sudden kind of transition here from being 5 to 8,000 K to being more than 15,000 K towards the half of the lifetime or so. And this has to do with a drop in density. And when you drop the density, your collision frequencies drop down, your antipolar diffusion increases, but essentially the slippage between the neutron and the ion population increases. And that can lead to very strong dissipation of electrical currents. And that's exactly what happens here. So you get very strong heating because of the electrical current and because of the antipolar diffusion. And the electrical currents are the ones that are generated as part of the whole formation process of the specules. The key in testing whether this model works is not just looking at the physical variables and saying, oh yeah, they're 50 to 100 kilometers per second and they have some heating. The key here is to look at synthetic observables and compare them to real data. And that is where in the past that model, I remember I mentioned that we had a paper or 2 papers on that spicule. It kind of failed when we started looking at the synthetic observables. These new spicules here in this simulation don't fail, they actually match the data very well. So this is calcium, magnesium, and silicon-4. And these are from the simulations, synthetic, and here the bottom panels are 2 examples from the observations on the SSD. And in the SSD, these spicules show up as very strongly blue-shifted features that are in absorption in calcium, kind of an emission in magnesium, and definitely an emission in silicon-4. And we see very similar features here. So that was very exciting. There's also a prediction here that you'll see something in the corona, and we'll come back to that. Before we get to the corona, let's talk first about the transition region. So one of the things that has really puzzling us for a while since IRIS was launched and people started looking at these network jets, these kind of transition region counterparts of the spicule that you see shooting through here. You see these bright points, these are network elements, and then you see these linear features emanating from these bright points. They have speeds of 100 to 300 kilometers per second. This is from a paper by Diam and his student. They're very, very high speeds. When you look in an active region, you actually find some evidence for, again, this is a movie here, this is a space-time plot in that white box. So this is space and this is time. And you can kind of see a spicule here, there's like a parabola here. Well, on top of that, you see these very rapidly occurring silicon-4 spicules. And they form over their whole length within just an exposure or 2. So they're very, very fast also. They're 100 to 300 kilometers per second. And they seem to form on already formed spicules, these particular cases here. It's hard to see in quiet sun and coronal hole because you don't, this is a walk plot here. The signal is actually very, very faint. And presumably that's the signal of the classical transition region at the top of the spicule. And what you're seeing here is something else. And it's definitely not what you see when you look straight down on these spicules. When you look at the Doppler shifts there, there's a huge discrepancy. We have these apparent speeds of 100 to 300 kilometers per second, yet the Doppler shifts are never really larger than 100 kilometers per second. They're typically 50 to 70 kilometers per second. You can see some of that here. These weak signals here are spicules in carbon-2 and silicon-4. So how do you reconcile this? Well, it turns out the model helps us with that, because in the model, we also see in this movie here, temperature and silicon-4 intensity. And you will see here in the silicon-4 intensity that as the spicule forms, there's these red, very thin linear structures that form very rapidly. They don't last particularly long here, but they form very rapidly. They are caused by increases in temperature, which are caused by electrical currents shooting through the spicule. So the spicule gets formed, the currents go through the ambipolar diffusion, dissipates the energy, and it leads to heating, the transition region temperatures. And so what we're actually seeing in the model, and also in silicon-4, you can see that here, this is the space-time plots. This is time, this is space along the spicule here in silicon-4. We see, just like in the data, something that appears at extremely high phase speeds, several hundred kilometers per second, that forms over quite a length here. And in the model, of course, we can analyze why this happens, and they're essentially heating fronts caused by the propagation of electrical currents at alpha speeds. So the apparent motions that you see are not always real mass motions, and the latent spicules are actually just heating fronts. In our model here, they would be caused by currents that are dissipated by ambipolar diffusion. All right, so this I've seen. This might also explain some of the very high apparent speed that we see in calcium spicules. That's something to be studied further. And of course, it affects any estimates of kinetic energy or mass flux in spicules. If you do it based on these transition region jet-like features, that's probably not a good idea. So let me finally get to whether there's any coronal heating associated with these spicules. And we first started with an observational study that we started a long time ago, and we never really had time to finish. It's the work done with Scott McIntosh and William Mortal. And we've known, of course, for a very long time already, since the trace days, that these coronal loop structures that you see here in 171, when you do a running difference on these, so in other words, you take an image and you subtract the previous image in the time series, you accentuate the rapid changes, and what you find is that there's these coronal propagating disturbances, or propagating coronal disturbances, PCDs, we call them, shooting out from the foot points and shooting along the loops outward. There's been a lot of discussion about these, and when the loops are rooted in sunspots, it's clear that they're related to waves, to sound waves. The Umbra has a lot of sound waves, and they clearly make it into the corona as well. It's not so clear in plage because the signals are not very periodic. They're really only quasi-periodic. And as I will show you in a minute here, it's not always clear that they really are just a disturbance passing through. So one of the things we wanted to do now that we have irises, we have AIA, we have iris, is all of these little spicules in here can be connected to there. And this is a very big, challenging task because you have so much superposition in the corona. The transition is a little better, but there's still a lot of things going on at the same time. But we think we found several examples now, and this will be a little bit suspension of disbelief. I'm happy to show you this on my screen later. There is a spicule in here. You can see the bright blob that's part of it, but there is more emission that's linear too, that shoots out here. The running difference also shows a signal that shoots out at the same time. You can see this a little better in this plot. This is now time. You can see that here. The spicule forms, and as the spicule forms, you get a signal that very rapidly propagates along the coronal loop. And there's another example here, where again, there's a spicule forming in that box, and there's a similar feature forming right here, shooting out. When we go and look at these signals, it's all running difference, and it's kind of pushing the noise levels of the data. When you play around with color tables, you actually realize that These are not just propagating disturbances, they actually are, it's the formation of a loop strand that seems to be associated with these spicules. And you can see that more clearly here. You see the time running here, and you see this particular thing here is actually associated with a spicule that we saw in iris. And it looks like a PCB when you use running time difference, but it actually is a new loop strand that forms and sits there for 15 minutes before it moves down. So we think that there's observational evidence that suggests that these spicules have coronal counterparts. And we think that that's actually formation of new loop strands. When we go look at the model, we find actually a very good match to that. We see here 171, 195 emission, here's the temperature, density, and joule heating. And within that white region here, we have, again, we're going to do space-time plots, but that's where a spicule forms. You can see it form right in here. And when it forms, the electrical currents that are associated with the formation of the spicule propagate into the corona. And when they propagate into the corona, they lead to heating, and you can see the temperature increase here. And that leads to a signal in 195 and 171. These are two AIA channels dominated by iron 9 and iron 12. So when you look in that particular region, you find a few different things, a lot of different things. So this is now distance along the loop, and this is time. You can see in the temperature that there's two things going on. There's a feature that's relatively propagating relatively low speeds and one that propagates at much higher speeds. You can see in the 171 emission, it looks a lot like what you see in the running time difference kind of space-time plots that people have been looking at for decades now. So it looks like a PCD. But in addition to that, you see this joule heating happening here. So we see a few different things. The spicule leads to a propagating shock wave, and that's this guy. It leads to strong flows at coronal temperatures, and it heats also, there's also heating throughout the volume and throughout the coronal volume because of the joule dissipation of these currents. So these currents get into the corona and they dissipate it by the BFOS model, of course, numerical resistivity. But it leads to these coronal side effects. Now, how general and how important this is for the full coronal balance, we're still looking into in the model. There's clearly also heating that's unrelated to spicules in this model. So we're certainly not claiming that this is doing everything, but it's interesting. So spicules are essentially a signature of coronal heating. Now, the reality of what really happens in spicules in terms of dissipation of the energy probably has to do, this is my last slide, has to do more, or may have to do also with the variety of wave modes that we also heard about yesterday. And people like Patrick Antonin have done simulations of prominences where they have transverse modes and they couple to azimuthal modes, and you get a Kelvin-Helmholtz instability, and that can lead to dissipation of wave energy. Something like that might be happening in spicules too. It's very, our model is not sophisticated enough to do this. These kinds of models are much higher resolution, but of course they lack many other aspects. But I think it's very worthwhile to investigate further these observational studies to look at the variety of wave modes and how they get damped. So in conclusion, I'll just leave this up here. The outstanding issues I wanted to briefly mention. It's not clear how well this will work in 3D, and so we're working on that now. We have not included non-equilibrium hydrogen and unit ionization. We already talked about the wave modes, and we're still thinking about this. But another aspect of this is that we're using this generalized Ohm's framework, and it's very likely that once you do this in multi-fluid codes, that you find a variety of different things. So this is just the first step. Thank you.
Good morning, everybody. So first, I thank Timur Zakarashvili and colleagues for inviting me here in this conference and to give a talk here. This is a brief review kind of talk from my side, and basically I'll be talking about the development in observations for detecting orthogonality in the solar atmosphere and how it is getting established slowly that they can serve as a potential energy source to fulfill the polar losses in the atmosphere. Yeah, so we are aware with this that corona and its emissions as well as energetic particle generation, they all tell about its high temperature. But still we are not aware that what are the candidates that can lead to this much hot atmosphere, how the energy losses can be overcome by several candidates, or mechanism. So this is the quest on which people are looking for since long. It is also well known to us that two broader perspectives are known to us, and one is the direct dissipation of currents by the magnetic reconnection that can lead some energy and kind of preheat the atmosphere, and another is the competing mechanism, and that is alternating current heating, which basically leads to the various wave modes. And as we are aware, we are knowing about various wave modes like slow fast metavasty waves. But basically, since last 2 decades, our concern has grown towards the one wave mode, which is alpine wave, that is transverse in nature. And as far as when we go and understand it in isotropic plasma, this is the transverse motion of magnetic field lines, where velocity perturbations are perpendicular to the wave propagation. And it is established fact that these kind of waves can carry sufficient amount of energy up to longer distance. And if they are getting dissipated or they are somehow converted in other forms, so they can act as a local energy source in the inner solar atmosphere, inner corona, as well as in the lower part of the atmosphere. So once it was known to us that these waves can serve as a potential energy source, so quest started with their detection. And I will not mention about pre-SOHO era, when several measurements were done by Donald Hansler and other colleagues. But I will start with one significant observation in Sumer era, like SOHO-Sumer era. And that was the silicon 8-line broadening, and it was observed over the polar hole. And you can see when they convert this line broadening in terms of non-thermal waves, so they were getting its increment and the plateau formation with the height in the polar corona. And as we know that in ionic equilibrium, all the line formation they must have constant width. They should not increase in terms of its line width, but it's happening here. And then they fit with the linear model of olefin waves on that time in that unresolved part of the corona. And what they got that this unresolved fluctuation of velocity, which is the least velocity, which was related to the non-thermal velocity in the that was fitting with the B minus 1 by 2 as well as rho minus 1 by 4. And this they claimed as a signature, indirect signature of olefin waves in the isotropic corona. Because at that time we were not having much clues about the resolved structures in the corona. And that was very intriguing observations on that time, 20 years back. And when we recall the development of those knowledges, so we find the competing observations with CDS, which was also on board on that time and working with the SOHO. And they did the similar kind of exercise with magnesium 10 line, but in the equatorial corona. And this was the scenario at the equator. And what they found, when they detected the magnesium line wave, they were getting its decrement. And on that time, they proposed, along with Alan Hood, that these are the several loop strands they are feeding the corona. And in each loop strand, there is an evolution of olefin wave due to foot point rotation. And since these waves are detected at these detection point with the height, so what they were getting, they were expecting that there should be something in terms of amplification, because density is getting decreases with the height in various part of this detection point. But instead that, they got line width decrement, and then they took some model with the effect of magnetic diffusivity as well as viscosity that they took into consideration, and that was a simple model. And with some analytical analysis, they got that velocity squared of olefin wave that is also showing similar pattern what they observed in terms of line width. It should be reminded that at that time CDF was not having instrumental slit width, so they could not convert it in terms of non-thermal velocity. But anyway, this was a line width decrease. So these were earlier findings, and that were showing something about the prediction of olefin waves. And people are believing that olefin waves, when they propagate along the magnetic field lines, they can polarize in 2 degrees of freedom, and they can contribute in an unresolved manner to the velocity fluctuations at a detection point in the corona at several heights. So, but these were landmark discoveries on that time in Soho era, because on that time we were not having much evidences about spatially resolved or highly resolved, in some sense, coronal or other atmospheric structures or magnetic structures. Here recently we did similar exercise, but with EIS observations. Likewise, those classical experiments, and we took the slit, we took the observations along the polar coronal jet, and what we got some typical polar coronal jet here, and there was a Doppler blue shift, and there was some variation of line width there with iron 195 line. And you could see here there was a high line width at the full point, and there is some variation of the line width along the jet. And you can see here what we got after several heights, when the bright point was visible at the base of the jet, we got increment in the line width of iron 195, and there is variation in intensity. Of course, it is decreasing because we are going away from the pole, and there is a conversion of red shifted foot point towards the blue shifted spiral. So this was a typical jet observations in a spectroscopic point of view, and what we are getting that at coronal height in the inner corona, suddenly red shifted loop, which was small scale loop at the jet point, it was converted in blue shift. That was jet plasma is flowing along its spine line, and on the same time with the height, what we are getting the increment in the line width. And you can see the fitting of those lines and our measurement. And what we propose, likewise previous Soho experiments, that this could be the possible signature of the unresolved motions, non-thermal motions, which are added to the iron line, and and that could be due to the olefin wave. What we did then, we put some numerical simulation in the jet type of configuration. We put here magnetic ray connection at certain height, and then we got the evolution of olefin wave velocity. And what we did, we averaged spatially these velocity signals, and then we generated by some calculation this synthetic green one, synthetic line profile and related wave. And what we could find, along with the spatial height along the jet, this was showing the similar pattern of line width values. So we tried to say that since these jet structures are somehow seen in the ice spectroscopic observations, and that could be the signature of the evolution of olefin wave, but impulsively after the reconnection. So these were the indirect observational detection of olefin wave on that time. But as we can recall, that after trace, we got many resolved structures in corona and in form of high resolution magnetic structures, and then we were trying to understand the individual motion of flux tubes and various tubular wave modes like kink mode, sausage mode, and sorry, it's not working, torsional olefin modes. So they were the natural solution of tube MSG modes, and these were associated with fast multiacoustic waves, while one was true incompressible torsional olefin waves. Once spatial resolution came into existence, so there were several discoveries claimed by Hinode, and you may recall these discoveries about the olefin waves, like in prominence, solar wind, in X-ray jets, as well as species. And they are transverse motion of magnetic flux tubes, magnetic threads, and they are claimed as an olefin wave because they were showing transverse motions on that time, and the period was several hundred seconds. Later there was some debate about the kink on olefin wave scenario, but then it turned that in highly structured corona, even if the tubes are transversely structured, there is a possibility of mixed mode, and they are termed as olefinic waves. And apart from those Hinode discoveries, there were several observations by various workers and colleagues about the generation of olefinic waves in various kinds of flux in the solar atmosphere. So this was the another kind of development, and that were giving the clue that of course tube modes, various kind of tube modes can excite in individual tubes, but when they are put into the highly complex solar atmosphere, there is a possibility of the generation of mixed mode, and one kind of mixed mode in terms of olefin wave is the olefinic wave. And then there was simultaneous development of theoretical models by Bussens, and colleagues, and they were discussing about the generation of olefinic modes. And those modes were somehow like the coupling of radial velocity perturbations, that are kink mode, as well as azimuthal velocity perturbations over the tube in certain resonant layers due to this kind of transverse plasma and magnetic structuring. So they got it at the resonant layers across the tube, and those mixed mode, they were coming into existence through the various observations. But I already showed some olefinic wave observations recently in the SPQs. So these are the refinements of theory as well as observations as far as we concerned about the detection of olefin waves in the complex solar corona, which is of course structured. In between these claims, there are some claims about the detection of pure olefin waves. So this is the claim by SST observations, and that is using core of H-alpha line profile using SST spectropolarimeter. And David Chase and colleagues, they have talked about the generation of some periodic variation of lines in triad, because they were observing the core of H-alpha over the bright point in chromosphere, and they termed it, you can see here the periodic variation, that at the edges of the bright point, they got 180-degree phase changes over these bright points. So they told that flux tube is associated with strongly magnetized bright points, and there are torsional motions that may occur in an isolated individual tube, and they are giving the observational signature in the SST observation. So it was a unique example in that time about the long period detection of torsional motions in the tube. So as you can see, starting from detection of olefin wave unresolved or less resolved solar atmosphere by the line width exercise and so on. Now we have gone towards the mixed mode detection in terms of olefinic wave, and there are one detection which is talking about the pure axisymmetric m equals to 0 olefin torsional mode in the bright point and associated flux tubes. We tried then in our recent work, which is claiming that we have detected several finely structured flux tubes through SST observations. You can see these flux tubes, and they were appearing like integrated bunch of fine structured threads. Like when we see in the current resolution of AIA, and other past observatories. So they will look like an integrated single flux tube. But with SST resolution, we were getting this kind of fine structured flux tubes. And what we are trying to do, the field of view were here. And what these were trying to do, these were trying to do some periodic motions in terms of Doppler variations, like this. So there could be two possibilities. Either these fine structures, they are moving non-coherently, or they are moving azimuthal way, but as an integrated tube. So this is something like situation that you have single tube and you are feeding various fine wires, and at surface, the surface is doing collective azimuthal motion, and the period was from 24 seconds to 78 seconds, as I recall, and we termed it high frequency. It's a relative word, but we termed it as high frequency because these were directly detected towards the lower period range, and there were plenty there in that region where we observed the sun. You can see here. I already told about the possibilities here. So background atmosphere is very dynamic, but we isolated, we subtracted those background motions, and then we do some numerical experiment, just this simple experiment in 3D model structure, and we put azimuthal driver with the observed period of 50 seconds, and we are getting the excitement of torsional motions there. And then what we tried to do, we spatially averaged V theta mod square, and then we termed them as a contribution at various heights. We tried to calculate their contribution at various heights, and in terms of energy flux. And what we are getting, of course, some nominal effects are here, but we are getting that even after the reflection from transition region, which is inherent in the model, we are getting sufficient flux that is crossing transition and trying to interact with the corona, inner corona. So we could not understand about the dissipative process because our model does not include dissipative agents, but we termed them that these kind of structures, they possess torsional modes with lower period, and they can carry sufficient amount of energy upward, and they can serve, if somehow dissipated or converted in some other form, they can serve as a possible energy source to the inner corona. These are the conclusion on the development I already told. So we started with the consideration of orphan wave as a possible energy source. Our quest was to serve those orphan waves. So has contributed in a remarkable manner about the early detection of orphan waves, and then there was a detection of orphanic waves and other wave modes in terms of high resolution observations from Hinode, and of course later by SDO and IRIS, and then some ground-based high resolution observations. We are carrying out the excitation of pure orphan modes at different frequency range, and all they simultaneously can be considered as a high energy source or remarkable energy source that can serve to heat the solar atmosphere locally if they could be dissipated, or if they could be dissipated by some non-classical manner by phase mixing or some other mechanism. So that's the conclusion. Few advertisements like this Indian Aditya L1 space mission timeline is 2019, and we have solar ultraviolet imaging telescope, PELC, and some high energy experiments there. And as we can recall, that solar orbiter is coming in 2019 to us, and several ground-based observatories will be there like Ricky. So that will be the high time to coordinate with the various, in terms of various observatories, including Aditya. Probably you are aware with that, and this is another advertisement about a conference. This is Dynamics and 2, and we organized Dynamics and 1 in Varanasi, in 2016. Many of you were there. And next one is coming under the leadership of Zambia and Sheffield in Cambodia. So that's my conclusion.
So as we have just seen in the previous talks, alphanic waves are observed everywhere in the solar atmosphere. They are ubiquitous, and this kind of waves are to be driven at the photosphere, where the photospheric motions can drive these waves, which later propagate upwards to the corona. The very presence of these waves is very important because energy estimation suggests that this kind of thin waves can carry sufficient energy to maintain the temperature of the solar atmosphere. But of course there are still a lot of questions under debate. And in this work we are going to focus on these two questions that I have written here. In the first place, we are going to study how are the reflection and transmission properties of the waves as they propagate from the photosphere to the corona. And in the second part of the talk, I will show you some results regarding the dissipation of these waves, and that I will discuss whether this heating produced by the dissipation is efficient enough to compensate the relative losses of the plasma. In both cases, we are interested to know if the expansion of the magnetic field plays a role. So as I said before, we are considering a simple model that aims to represent the gravitationally stratified low solar atmosphere in which there is an embedded magnetic flux tube that expands with height. In this model, we consider from the photosphere to the corona and include the chromosphere and the transition region. And as I said, in this background atmosphere, we embed a magnetic flux tube which expands with height. We are interested in studying the propagation of torsional alpine waves that propagate a long tube from the photosphere to the low corona. Concerning the variation of the physical properties of the plasma with height within the flux tube, we are based on the well-known models from Fontaine et al., which we have extended up to 4,000 kilometers over the top of the photosphere by representing the low corona. We are going to assume that the plasma is composed of hydrogen and helium. Both the species are partially ionized, but we assume that all the components of the plasma have the same temperature. So on the left panel, I display the temperature in the model as a function of height, and on the right panel, I display the total density of the plasma. The four different lines correspond to the four models that are given in the well-known paper by Fontaine et al. Concerning the magnetic field model, we are going to assume the thin flux tube approximation, in which it is enough to prescribe the vertical component of the magnetic field. Because of conservation of the magnetic flux, if we know how the vertical component of the field varies with z, z is the vertical direction, then we know how the radius of the tube varies with height. After this paper by Lick et al., we are going to prescribe the vertical component of the field using this simple formula, which relates the decrease of the magnetic field strength with height with the decrease of the density through this power law expression, where epsilon is an arbitrary expansion exponent. On the left panel, I display the magnetic field strength as a function of height according to this formula, and the different lines are for different values of the expansion exponent. The top line corresponds to a weak expansion, and the bottom line corresponds to a strong expansion. On the right panel, I display for the same parameters how the radius of the tube expands with height. So to study the propagation of torsional waves in this model, we are going to use a version of the multi-fluid equations in which all ions are considered to be strongly coupled. So all the ions form a single ionic fluid, but we consider separate equations for the two neutral components of the plasma, and we allow these ions and neutrals to collide. So there is in our model a dissipation mechanism that is these ion-neutral collisions. These collisions will damp the alpha waves that propagate in our flux tube, and the energy dissipated by these collisions can be used to heat the plasma. So these are the basic equations we are going to use. These equations are linearized because we are studying alpha waves in a linear regime. So, and because we study torsional waves, we are interested only in the azimuthal components of these equations. In addition, we are going to consider the stationary state of wave propagation, so we are going to introduce the wave frequency, and we are going to work in the frequency domain. So we can combine these multi-fluid equations, and after some manipulations, we arrive at an equation that governs the propagation of the wave. It's a very simple wave equation for the azimuthal component of the velocity of the ions. All the terms in this equation depend on the vertical direction only. What is important here is that we have this term in red, this omega pole, which is a complicated expression that contains all the collision frequencies between the different species that form the plasma. So this term contains the effect of the dissipation. In addition, we can obtain an equation that describes how the energy of the waves evolves with time. And this equation tells us that the energy density of the waves changes because there is a propagation of energy with the Poynting flux, and also there is some dissipation of energy due to ion-neutral collisions. So in our method, we are going to assume that we have an incident wave and the bottom boundary of our domain. This is at the photosphere. And at the same time, at the same boundary, we are going to assume also that there is a reflected wave. So we can define the reflectivity as the fraction of the incident wave energy that is reflected back to the photosphere. This is just computed as the range of the Poynting fluxes of the two waves. At the top boundary, we consider that there is a transmitted wave, and we define the transmissivity as the fraction of the energy that is transmitted to the corona, which is computed in a similar way as the ratio of the Poynting fluxes of the transmitted and incident waves. And since there is some dissipation in our model, the sum of the reflectivity and transmissivity is not equal to 1, and this difference is just what we call the absorption. Is the energy of the incident wave that is deposited in the plasma. So we have implemented a numerical routine that solves the wave equation in this model, and as a function of the wave frequency, give us the values of the reflectivity, the transmissivity, and the absorption. And these are the results. I display here the reflectivity, the transmissivity, and the absorption as functions of the frequency of the incident wave. These results are computed for a fixed magnetic field configuration, but the different lines represent the 4 different atmospheric models we are taking into account. In all cases, we see that for low frequencies, reflectivity dominates. This means that most of the energy is reflected back to the photosphere, but as the frequency increases, the reflectivity decreases and the transmissivity increases. This means that more and more energy is efficiently channeled to the corona as the frequency increases. But then, if we keep increasing the frequency, we see that the absorption starts to grow, and for sufficiently high frequencies, all the wave energy is absorbed into the plasma. Here we obtain some differences for the 4 different atmospheric models. This is because the absorption is directly controlled by the value of the collision frequencies, and these collision frequencies depend on the specific physical parameters we are considering in the chromosphere. So what I'm going to show you now is the same results as before, but for the same atmospheric model and changing the value of the expansion exponent. So this is again the reflectivity, the transmissivity, and the absorption. And now the different lines are for different values of the expansion exponent. The top line here corresponds to weak expansion, and the bottom line to a strong expansion. And we can see that the effect of the expansion of the magnetic field is to decrease the reflectivity and to favor the transmissivity of waves towards the corona, while the effect of the expansion of the field is not very important in the case of the absorption. It is important also that the maximum of the transmissivity is shifted towards lower frequencies when the expansion of the field increases. Now I move to the second problem I wanted to discuss here, which is the heating caused by the dissipation of these waves. So what I'm going to do now is to consider all the waves that we have in our frequency range, and to sum the contribution of all these waves, to sum the heating produced by all these waves. To do so, we have to assume some more things. First, we have to assume a value for the incident point in flux at the photosphere. We take this typically assumed value. And another thing we have to assume as the power spectrum of the waves at the photospheric level. And we use this simple power law dependence that has been used also in several papers in the past. These are the results of the computation of the heating rate as a function of height for different values of the expansion exponent and for the fixed atmospheric model. Here, what we can see is that if we increase the expansion of the magnetic field, the heating rates become smaller and smaller. This is so because, as I said before, when we consider strongly expanded, when we increase the expansion of the magnetic field, more and more energy is efficiently channeled to the corona. So less energy remains trapped in the chromosphere to be available to be dissipated. Now if we compare these numbers with the values that are required to maintain the chromospheric temperature, we can see that we obtain quite similar values if the expansion is not very strong, but when we consider strongly expanded fields, the obtained heating rates are much lower than those that are required. Finally, I will show here the same results, but now I keep the magnetic field configuration fixed and I change the atmospheric model. Here you can see that there can be important differences between different atmospheric models. The heating rate can vary up to 2 orders of magnitude. And this is so, as I said before, because the dissipation of the waves depends a lot on the specific physical condition you are considering in your model. So, even for strongly expanded tubes, we can still obtain quite efficient heating for some combinations of parameters. So these are my conclusions. First, regarding the reflection and transmission of the waves, it seems that there are 3 different propagation regimes. Low frequencies are reflected back to the photosphere, intermediate frequencies are efficiently transmitted, and high frequencies are the energy of high frequencies is deposited in the chromosphere. When we analyze what is the effect of the expansion of the magnetic field, we find that transmissivity is enhanced a lot by the expansion of the field, and the maximum of the transmissivity is shifted towards lower frequencies. Finally, when we compute the heating rates, we obtain heating rates that are usually smaller than the required rates, but they depend a lot on the physical parameters in the atmosphere. So, thank you very much.
My talk is about methods and instrumentation. I've got the models, but anyway, I think and I hope that this will be interesting for you. This is a new thing. Maybe now it looks seems mysterious, like the sun is, but I think finally we will find that this is quite interesting. So we are doing this work with colleagues. Thanks to our colleagues. Well, how it was beginning. A little bit, a few words about history. This gentleman is Professor Sherzan Kakichashvili, who in 1972 first time developed and studied the polarization holography, both the phenomenon and method, which is the basis of everything we will talk about now. And here is the references. You can find them. Unfortunately, most of them are Russians, but anyway, it's interesting things. So, something about philosophy and basic phenomena which we use. So, first thing is that we need, and fortunately it is possible to develop and design some kind of polarization sensitive materials or medium which is responsible to the polarization of incoming light. And beside this, it has a characteristic of behavior to record and, more important, to store full polarization state of incoming light. So further, as we are storing this information, it is very important to restore or get back the information which was stored inside this medium, and doing whatever we like, measure or recover something like different. And as the outcome, and the most important is that we can design and record special polarization state light patterns, which we called, and is called now, polarization diffraction gratings, which will modify diffraction order intensities of incoming light with arbitrary polarization state. And finally, it is very also important that polarization gratings recording on the same area of polarization sensitive materials are absolutely independent of each other, so you can have gratings in a one 3D medium and there will be no crosstalks or influence with each other, and the diffraction order beams from each grating are spatially divided. So this is a philosophy of our instrument, of our methodology. By the way, and many of these issues also were found and studied and developed by Professor Kakichashvili first time. So a little bit about chemistry. I'm very weak in chemistry, but anyway, to show you what happens inside on the molecular level inside this medium. So when you radiate the medium with the incoming light, there is some kind of cis-trans isomerism which changes molecular state inside the organic molecules. And you see here that the first side of this organic chain changes its configuration. So this phenomenon also, and the upper part is very simple representation, of course, but really in the reality we have very complex distribution of tensions and structures and so on. So we have a group of centered in the molecular level, centered around the tension centers, and then we have a cross links between the chains and so on. So quite difficult structure inside the material. But anyway, the schematic show we can see that these kind of changes in molecular structures behave in that way, that it changes the incoming light polarization, and then we have some kind of effects there. So Well, about diffraction gratings, we use 3 polarimetric diffraction gratings. First, it's a C or circular type grating recording with 2 orthogonally circularly polarized beams. I mean left hand and right hand. Well, this is the schematic view of phase differences and also the wavefront. The second grating is a L90 or linear type of grating recorded with 2 parallelly linearly polarized beams having azimuth of 90 degrees. Also, you see the schematic view of this grating. And the third grating is L45, or the similar as the previous one, but with an azimuth of 45 degrees. So, what we get here, this is very interesting for this slide. Of course, this is a CCD image diffraction orders when we used a laser beam in the laboratory tests. So this is a schematic view of outcome of what we get with these gratings. So as soon as we have a diffraction gratings, we have diffraction, of course, and we have diffraction orders. So we have 0 diffraction here, and the first order diffractions. And the intensities of these orders is the most important for us. So that's what we are using in getting the final results. Well, this medium or material we are talking about finally forms a polarization holographic element. That's the main optical element used in our setups. And it has some kind of parameters, of course. The spectral range is 500 to 1600 nanometers, but this is not a limitation. The 500 is a lower limit because during the recording we are using blue lasers, but actually if we will use lower, I mean ultraviolet lasers, we can shift the lower limit to the blue region, of course. The second, we can say that current aperture is 20 millimeters, but also it is not a limitation, so we can increase whatever is reasonable. And the diffraction efficiency, which is very important parameter, so we have about 20%, it's the best we can achieve at the moment. But also this is not a limitation, the development is ongoing, so we hope to increase the efficiency. So we have 20% of diffraction efficiency in the green, and 16 in the red, and about 2% in the infrared. And diffraction gratings density is at 330 lines per millimeter, it's about this one. And as soon as we have diffraction, we have a spectral dispersion, of course. So in the current first realization of our instruments, we have about 70 nanometers per millimeter of spectral dispersion. Well, a few words about how we get to this stock vector. Well, authors, our colleagues, built this model. So finally, we can see that we can go from the right side intensities finally to the Stokes parameters, but depending on position and the wavelength of incoming light. So, and what is very important that these relations are linear. So we can easily calibrate the setup and go from the intensities. So I's are the intensities in the different diffraction orders, and the K's are the coefficients, which are depending on the wavelength, of course, and on the current elements or current setup. So we can calibrate easily and go to the Stokes vector. Well, we tried to build a first setup, or first version of this polarimeter, or prototype of, we can say, prototype of this. And you can see how simple the design we can achieve using this kind of methodology and the polarization holographic element. Actually, the most important part of this polarimeter is the elementary, and other things are just an addition. So what we have here, the telescope, the input diaphragm or slit, whatever you like, then the collimating lens to have parallel beams, and then filter, or optionally no filter, but that depends on realization, the elements, objective, and the CC camera. You can see the silver color tube. This is the polarimeter actually, so the black one is a CCD camera. Okay, I will try to pass very quickly. Well, we try to use this polarimeter for the solar spectropolarimetric studies. Well, that's a nice picture, but very robust telescope. It's a 53 centimeter large non-eclipsing coronagraph of Abyssinian Astrophysical Observatory. So you see here a 53 centimeter objective. Here is an artificial moon, and then light goes to the CUDA focus. And you see spectrograph of our coronagraph. So that's the slit, and inside the room is other optics, and we see here our spectrograph, polarimeter in the plane of coronagraph. There are some parameters for this, about 1 angstrom per millimeter dispersion in the H alpha, and about 0.03 angstrom of resolution, and well, some test diffraction, polarization diffraction images in H alpha. In H alpha you see here, and in the three H alpha images we have taken in 2016, September 8. Exposure time is 10 seconds. Well, what is here in that direction, on the about parallel, tilted, a little tilted to the X direction is a dispersion, and on the orthogonal way direction there is a parallel solar ring. So this was very fortunate. We are lucky to get this picture because the spicle is quite isolated, so we can easily process this data. Unfortunately, this year, 2017 September, this is the 3 images. The exposure time is 5 seconds, but the images were not very good because the scene was quite low. So, but anyway, we get this data to have some test processing, and what we get for H alpha, this is the Stokes profiles. They are calibrated for the wavelength and so on, normalized. So we see that there are some signal of in the V Stokes parameters and in Q and I. Unfortunately, not so good data in the D3, but anyway, there are some signals captured by these polarimeters. So finally, to have a conclusion, what is the advantages of this kind of realization of polarimeter? So it is universal. This means that you can use in different setups, like, for example, spectropolarimetry like this case, or used for night observations of variable stars, which we are planning to do, or in other things. You can use it on the ground for large or small telescopes, or even in the space. So universal, very compact, because so you are not using electric things, you are not using any kind of modulation, so you have only one element, optical element, which doing everything. Very simple in design, user-friendly, everything is coming from the other things, and fast and accurate, because there is no limitation in time. So if you have very fast CCDs, and you are just limited with the readout time of detectors, and finally cost-effective, because everything is very simple. Okay, that's all. Thank you very much.
Well, thank you very much to the Scientific Organizing Committee for inviting me to speak on this topic. only 1% of the sun's total energy is emitted at wavelengths less than 3,000 angstroms. So we may ask why should we worry about measuring polarization in ultraviolet lines? And the general answer is in order to investigate the magnetism and geometrical complexity of the plasma of the upper chromosphere, transition region, and corona. These are hot plasmas, temperatures above 10,000 Kelvin. The primary emission lies in the UV and extreme UV. It is, we want to investigate in particular the upper chromosphere and transition region. We need to take into account the problem of radiative transfer in strong resonance lines, because this is an optically thick medium for the lines that originate there. And in order to explore the magnetism, the magnetic field information is encoded in these so-called Stokes parameters, where each symbol simply is a filter that transmits lights as an electrical symbol. So we need to measure this linear and circular polarization in addition to intensity, and to observe and to interpret the observation. The physical mechanisms that control the polarization of ultraviolet spectral lines are these ones. Very quickly, I will go through them. The Zeeman effect polarization is produced because of the separation in wavelengths between the pi and sigma transitions that originates because of the Zeeman splitting of the levels. Important to remember always is this ratio, the ratio between the Zeeman splitting and the Doppler width of the line, the thermal width, and it scales as indicated here. You see that in the upper chromosphere and transition region, the magnetic field tends to be weak, the temperatures are very hot, and the radiation they are produced in UV, so everything conspires so as to have that this quantity is much smaller than 1. And here you have that the circular polarization amplitude scales with this quantity, while the linear polarization with the square of this quantity. Since this is much smaller than 1, there is no hope to measure this. The only thing we may perhaps be optimistic to measure through the Zeeman effect is the circular polarization, but for example, for the Lyman alpha line at this wavelength, assuming a 10 Gauss field, you get value of 10 to the -4. So the circular polarization in UV lines is very hard to measure. Here you have observations from ground-based telescopes of the 4 Stokes parameters, I, Q, U, and V, in 3 spectral lines, in the near infrared, in the visible H alpha, and in the blue. Look at the lower panels, the circular polarization signal due to the Zeeman effect. You see these for the infrared line. You see less for the visible, and you see practically nothing in the blue, just because of this scaling here. However, we see every signals in linear polarization. Doesn't matter the red, visible, or blue, but these have nothing to do with the Zeeman effect. These signals are due to the so-called scattering polarization. Basically, the real physical origin of this is that the radiative transition produced by anisotropic radiation fields produce atomic level polarization, population imbalances, and quantum interference between the sublevels of any given atomic level, and then this gives rise to linear polarization. And remember that you do not need a magnetic field to produce this. If there is a magnetic field, then we have the Hahn effect, which modifies, it's a symmetry breaking, it modifies the atomic level polarization, and therefore it modifies the linear polarization with respect to the zero field magnetic field case, as you can see in this plot. There is an additional mechanism that I will discuss later, but the important thing concerning the Hahn effect is this equation that gives us the magnetic field strength for which we should expect a significant Hahn effect. This is the Zeeman splitting of the upper level, similar to the natural width of the level. And the natural width of the level is something which doesn't depend on the temperature. So it doesn't matter if your atom is in the refrigerator of your house or in the corona, and as compared with the Zeeman effect, which was the Doppler width of the line. For example, if you go to the magnesium K line, you have a good sensitivity around 20 Gauss, for Lyman alpha around 50 Gauss. For the silicon resonance line in the blue wing of Lyman alpha, you get something like 300 Gauss. And for the helium, ionized helium line at 3 or 4, you have 850 Gauss. Now, in order to deal with these things, we have to work with in the framework of the quantum theory of polarization spectral lines. And of course, I cannot explain this here in 10 seconds. The only thing I want to do is to remember the fundamental and monumental work that has been done in his lifetime by Silvio Landi Innocenti. And what we are doing here is trying to solve numerically the equations taking into account radiation transfer effects. So the physical mechanisms that one has to take into account in order to aim at a realistic modeling of polarization in UV lines are very complicated. We have to take into account the Young action of the Reynolds-Mann effects. We have to take into account correlation effects between incoming and outgoing photons in the scattering event, the so-called partial frequency distribution. We have to take into account quantum mechanical interference between the two upper J levels of spectral lines, for example, between the upper level of the K line and the upper level of the H line. And we have also to take into account the impact of the Doppler shifts associated with the mass motions of the plasma, the impact of this dynamical state of the plasma on the atomic level populations and quantum coherences between. And of course, we have to aim at taking into account the symmetry breaking produced because of the horizontal inhomogeneities of the model. The ideal thing is to solve all these, the problem taking into account all these physical mechanisms. We have to go step by step. First, we consider the case of the Hamilton-Zeeman effects, neglecting all other effects. Later, we ignore the magnetic field, but we took into account PRD and quantum mechanical interference. Later, it was possible to solve the problem taking into account Hamilton-Zeeman effects and PRD, but ignoring the J-state interference. And more recently, it has been possible to solve the full problem, but for one-dimensional models, and the 3D problem has been solved neglecting PRD and quantum mechanical interference between the two upper levels. So we hope that within the following 5 years to be able to really solve the full problem in full 3D. Now, summarizing, today we can do partial concerning the generation and transfer of polarized radiation. We can do partial frequency distribution in one-dimensional models, taking into account quantum mechanical interference between the two upper levels of the spectral lines, because they are doublets like H and K or Lyman alpha, including the Hamilton-Zeeman effects. Or we can do resolution of 3D problems, assuming complete frequency distribution and neglecting the quantum mechanical interference. And this approach, fortunately, is giving us a good approximation for modeling the line core of spectral lines where the Hamilton effect operates. Well, prediction for Lyman alpha, basically at the spatial resolution of that it is possible to reach with today's technology, around fewer seconds, 2-3 seconds, the predictions concerning the polarization due to scattering processes and the Hamilton effect in Lyman alpha are here summarized. At the line center of Lyman alpha, the linear polarization amplitudes should be smaller than 1%, and they should be sensitive by the Hamilton effect to these magnetic fields. And there should be, this was our prediction, a significant center to limb variation when moving from the center to the limb in Q over I. Concerning the line wings, the prediction was that we should see negative Q over I signals with very strong amplitudes, larger than 1%, and with a clear center to limb variation. And also, both in Q over I and U over I, we should expect also clear spatial variation because of the horizontal inhomogeneity of the These theoretical predictions motivated the development of the so-called chromospheric Lyman alpha spectropolarimeter. The team is here summarized, and I would like just to simply mention Saku Suneta, for having believed strongly from the very beginning in this project. Well, here is the optical design of the chromospheric Lyman alpha spectropolarimeter. You can see the details in this paper, so it's better if I go directly to the observation. This was one day before the launch, with part of the team here, and here is the real launch that took place on September 3, 2015. It was a cloudy day, but fortunately the sounding rocket went above the clouds. And here you can see more or less the situation. Once the telescope starts pointing to the sun, now start observing. This is the image, the slit jaw image. This is the slit of a spectrograph. We were observing with the slit 400 seconds from 20 arcseconds of the limb towards the big center. It reached an altitude of about 300 kilometers, and as you can see, the amazing stability that was fundamental to the success of this mission. And I will now show you the results of the wavelength variation of I, Q, and U. Okay, now this is the position of the slit. Where I'm going to show you results integrated over the 5 minutes, or practically the 5 minutes of duration of the class experiment. This will be the reference direction for stores Q. Therefore, Q will be this minus this, and U will be this minus this. And here you can see intensity, stores Q in two scales, plus minus 6% to visualize the wind signals, and plus minus 0.6% to visualize the line center signals, and the same for stores Q. I do not have time to go through all the interesting things that are here encoded, but let me just focus mainly just mentioning that the Lyman alpha is a strong emission line, that the line core originates in the upper chromosphere and the base of the transition region. And here you have stores Q in a scale that is plus minus 6%. Red is positive, blue is negative. You see that the wind signals are very strong, larger than 1%, and they are negative. You see the blue color, and the amplitude is increasing as you go from the tick center towards the limb. And this is in agreement with the theoretical predictions, as you can see here. Very weak signals in the line center, below 1%, and strong signals in the wings, which become stronger and stronger as we approach to the limb. These are the theoretical predictions. You can see basically qualitatively the same. As you go towards the limb, you increase the signals, and they are larger than 1%, and in the line center they are smaller than 1%. And very interesting is also this, that when we make the calculations neglecting the impact of the quantum mechanical interference between the two upper J levels of Lyman alpha, when we ignore the fact that in a scattering event, the photon goes through the two upper levels at the same time, then we get much lower amplitudes. The reality is this, and this is what Glass has confirmed. Glass has confirmed that this quantum mechanical interference plays a key role in producing the strong polarization signals. Now, the line center is where the information on the magnetic field is encoded, because the Hahn effect operates in the line center, and here we have very weak signals, below 1%. And as you can see, these signals are fluctuating around 0 from the big center towards the limb. They are smaller than 1% in agreement with the prediction, but surprisingly, they do not show any center to limb variation. So in order to understand, this is a very interesting surprise, that the understanding of this, I think, is very interesting, because it will allow us to discover new things that we didn't expect. So in order to understand this, these are the theoretical predictions for one-dimensional models. When you make calculations of the variation with the cosine of the heliocentric angle, the center to limb variation of the line center signal of Lyman alpha, it doesn't matter the model you use. Even if we use the 3D models of Matt Harrison, we obtain a center to rim variation at the line center of the Lyman alpha. So we need to stop a little bit and to try to find the physical origin of this enigma by using basic models. So in a one-dimensional model, doesn't matter if there is no magnetic field or if the magnetic field has a random acidity along do we have cylindrically, the radiation is axially symmetric. And if you have this situation which is axially symmetric, then you can show easily that this formula applies. You know the so-called Eddington-Barbier relationship that says that the intensity that we observe at the line center is approximately equal to the line source function at that point along the line of sight where optical length is unity. So this is basically the generalization of the Eddington-Barbier relation to the world of scattering polarization. The line center amplitude is given by this expression. Here is the anisotropy of the Lyman alpha radiation at the point in the model atmosphere where line center for Lyman alpha is unity. This is 1 minus mu squared. Is basically the cosine of the heliocentric angle, and this h is basically the Handley V polarization factor. If there is no magnetic field, h is equal to 1, and if there is a magnetic field, it is smaller than 1. So this formula applies if you have this situation of axially symmetrical illumination. However, and here you can see exactly what happens. No? If you see from the center to the limb, the Q ray has a center to limb variation. In fact, in this case, U is 0. Now, the reality is different. The reality is more or less as indicated in this 3D model, where you have that the transition region is a corrugated surface. So basically, the situation is something like that. And interestingly, at each point, this direction, which is the normal vector of the transition region, is interesting to note that as a first approximation, we can consider that because Lyman alpha core originates in a very narrow region, at each point there is axial symmetry around this direction, locally. So we can in reality apply the same equation but locally, where now this is the anisotropy of the Lyman alpha radiation calculated for this point concerning this axis, for this point concerning this axis, etc. Now the point is that if we use this, then the reference direction for Stokes Q positive will be changing. Here I have to choose one positive, one reference direction, different to this. So what we have done here is to rotate the reference system in order to express the Q over I and U over I, all of them in the same reference systems, namely in the reference system in which Stokes Q positive is parallel to the limb. And then you get this equation here, where you can see that the amplitude of Stokes Q over I and the amplitude of Stokes Q over I are scaled with the H factor. There is no magnetic field, H is equal to 1. There is a magnetic field, it is smaller than 1. And here you see all this expression that depends on the angle between the line of sight and the vertical, between the inclination of the normal vector, etc. So we can now make some numerical experiments. The limit of a plane parallel medium corresponds to the way in which the normal vector is always perpendicular. So we get exactly what we should expect, the center to limb variation. But now imagine, for example, that we take that the transition region is like that. This situation will be like cylinders. The full solar surface is full of cylinders going up. And when you do then calculate the limb variation, you get this. So this is very interesting because it's telling us that depending on the geometrical complexity of the transition region, we have different impacts on the center variation of the line center sequence of Lyman alpha. And if I now consider that this normal vector is chaotic, we get positive and negative values with no center to limb variation at all. And this amplitude here is depending on the strength of the magnetic field. This is for zero magnetic field. If I increase the magnetic field, the H factor, which is in front of the equation, reduces the amplitude. Okay? So, And now, what we are doing is to do numerical experiments in this 3D model that Matt Carson was showing us yesterday, applying the Porta code, which is suitable for estimating the original underlying center. The mean field strength in this model is around 15 Gauss. When you average along the corrugated surface that delineates the transition region. And this is what happens when for an observation at theoretic center when you assume that there is no magnetic field in the model. You get this amplitude at the line center for the total linear polarization. If you now take into account the Hahn effect produced by the model's magnetic field, you get less polarization as expected. The Hahn effect is depolarizing. And if you increase artificially the magnetic field, you get still less polarization. You can do the same for another line of sight for mu 0.4, where mu is the cosine of the heliocentric angle. And you put the magnetic field, you get less, and you increase more, and you get less. So now, very quickly, let me use this 3D model to make some radial realizations of the center line variation, taking into account the PSF of glass with spatial resolution. So this is what happens when assuming that there is no magnetic field in the 3D model. This is the center, this is the limb. You see that most of the signals are negative and there is a clear center to limb variation. If we take now into account the magnetic field of the model, the situation has to change a little bit, but still the amplitudes are predominantly negative. If we now artificially increase the magnetic field till 125 Gauss, then we start approaching more the glass observation. However, the sun is a wolf in sheep's clothing. We have to remember that the spectral line polarization, as I was showing before, is sensitive not only to the magnetic field, but also to the geometrical complexity of the plasma. And the 3D model of Matt Carson and collaborators is wonderful, but it's not the reality. So this model may not be representative of the complexity. In particular, it does not have speakers. No? So let us increase the geometrical complexity of the 3D model. But instead of using a bipolar diffusion like Martinez-Sikora, I am going to use a much simpler method, which is to squeeze the model horizontally. And I am able to create wonderful speakers of type 2, perhaps. No? So now let's do the experiment here. This is the situation for the original model before any compression. As you see, we have many negative signals and a center to limb variation. But if you compress the model artificially, you kill this center to limb variation and you start approaching reality. What we are doing now is, for a parameter space, for different magnetizations of the 3D model and for different compression factors, we are calculating for which combination of magnetic field strengths and geometrical complexity we end up with the maximum likelihood in a statistical sense. And we are finding that we need more magnetization than in the 3D model and more geometrical complexity. And this is natural because this model is building from the speakers. So we need 3D models of speakers, and the advance made by Martinez-Sikora and collaborators is a very welcome advance. Now, let me now remember what I have just said, that with one spectral line we have two things that are having an influence on the polarization, the magnetization and the geometrical complexity. We need to explore other spectral lines that have a complementary sensitivity, so that by combining two lines, well chosen, we may hope to end up with the solution to the problem. So let's consider basically what are our theoretical expectations for the polarization due to the joint action of scattering Hanley and Zeeman in the magnesium X and K lines. First, for a 1D model, ignoring magnetic fields, you see, this is the solution. You see very strong signals in the wings of the lines. They are a wonderful pattern. And if we now focus on the near core region, we find this with a sign reversal between the K line and the H line, with line center signals where the Hahn effect operates of the order 1.5%, with two negative peaks of the other -3%, something that we really can measure. We should be able to measure this much easily than with line analysis. And this is taking into account the physical ingredient of quantum mechanical interference between the two upper J levels. If we ignore that, we get something different, but fortunately, in the line center and in the negative peaks, this ingredient is not necessary. So this allows us to simplify the problem as a first step. Let us take into account PLD effects, the joint axiom of the Handler and Zeeman effects, and this new mechanism that I set in one of my first transparencies. So I am going to focus in this spectral area where we can ignore the J-state interfering effects around the line core of magnesium K. This is the transfer equation. We are solving the problem in full totality, but just let me point out that these terms here of the absorption or propagation matrix are the so-called magneto-optical effects. And because the symbol with index V scales with the splitting, with the Zeeman splitting, and the symbol with subindex Q and U scales with the square, these terms are more important than the other ones. And just to isolate the idea, if you develop the transfer equation for Stokes cube, you see that through this term there is a coupling with U, and the same happens with U. The transfer equation for Stokes U, through this term there is a coupling with Q. Only when you neglect this, as had been previously done outside active regions, then you do not get the coupling. So very quickly, let us see what happened for the magnesium K line with the scattering polarization of Q and U when taking into account the joint axiom of Handler and Zeeman, but ignoring this magneto-optical effect. So we see basically that everything, so without any magnetic field, of course you have in a 1D model that U is 0 and that Q has a line center signal and negative signals here due to PLD effects. But if you now take into account magnetic field, 5 Gauss, you see that everything is operating in the line center because the Handler effect operates in the line center. Okay, when neglecting these effects. But if we now take this effect into account, we have found something wonderful, which is this. Now there is also a magnetic sensitivity in the near wings of Q over I and U over I of the magnesium K line, already for very weak fields. Of course, because we were neglecting the quantum mechanical interference between the two upper levels, this simulation only applied to the line core region. And here you can see what happens when you also take into account the Zeeman effect. The Zeeman effect has an important impact on Stokes V circular, and here in the Stokes Q and U, you have the line core, the Handler effect, but in the nearby wing, you have the magneto-optical effects with the magnetic sensitivity. Since this line center provides information on upper layers, we have information on several layers in the solar atmosphere because here the opacity is less than in the line center. Now, if we take into account the quantum mechanical interference between the two upper levels of H and K, then we can go far out in the wings of magnesium H and K, the whole magnesium H and K together to see what happens. And here is what you can see in this numerical simulation by the Zimmerman and collaborators. The black line is for 0 Gauss. Here is the K line. The H line here, the negative in between as I showed you before. And here you have red lines for 20 Gauss for different azimuths. And here you have in blue 100 Gauss for different azimuths. And these symbols are all observations by Hense and Stenflo taken from the solar magnesium mission. They were able to measure only in the wings of the magnesium H and K lines. And you can see that even though this is a 1D model, approximately the modeling is able to reproduce the wings. The important thing is that, of course, if I investigate the magnetic field in these far wings, I am having information on the photosphere, on the magnetic field in the photosphere. But as I approach to the line core, I am going higher and higher up, till going to the upper chromosphere, where the center of the magnesium line is originating. So I am finishing. This is the ultraviolet spectrum. We have, with class 1, being able to discover scattering polarization in these two resonance lines. And we have shown already the theoretical prediction for the magnesium H and K, both the Handler and Zeeman effect in action. and this has led to a proposal already accepted by NASA, which is the second flight of glass. There is also a proposal being evaluated, led by HAO, which is to put these things in a mini satellite with another instrument, and the Sunrise 3 team, led by Max Planck, is thinking seriously in the idea of doing a spectropolarimetry between 3,000 and 4,000 angstrom. So these are my conclusions. Thank you very much.
Well, first of all, I would like to say thanks to idumali and to the whole organization committee for organizing such a nice conference at such a great interest. Well, today I would like to talk about numerical simulations of coronal waves interacting with coronal holes. That's actually what I'm doing during my PhD at the University of Graz, together with my supervisor Arno Kanzelmeier, and together with Bojan Brzunak from Zagreb University. I will talk about the simulations we perform with the code we developed at our institute. At the moment, we are especially interested in this interaction of coronal waves with coronal holes. And the question you could ask now is, why is it so important to study this interaction? Why is it interesting? So, for a short motivation, let's look at this running ratio movie, AIE running ratio movie, where we see an X-class flare and the subsequently evolving large-scale propagating disturbances. So, this red line represents the coronal hole boundary. And the interesting thing about this movie is, I took this from the Olmedo paper 2012. The interesting thing about it is that they stated it for the first time. You could see that these propagating disturbances are going through the coronal hole. So they're not only reflected or refracted, but they really go through it. So again, the question, why is this now so interesting? In general, we have these large-scale propagating disturbances all over the corona. They are everywhere. And there's already a long, ongoing debate on what they are exactly. There's one group of people which say, well, this is definitely true waves, MHD waves, which is kind of then proven by, let's say, effects like reflection or refraction. There's another group of people which support the pseudo-wave theory. This group of people say, well, these propagating disturbances are caused by, let's say, reconfiguration of a magnetic field, but they are not true MHD waves in that sense. And then there's another group of people who say, well, this is a mix of these two theories. What we want to do with our simulation is to support the wave theory. And I will show you how we do this. We have a very easy initial setup. We have pressure equal to 0 all over the whole computational grid. The first panel here is density, so we created an initial wave. All these numbers are dimensionless values. We created an initial value, and at a certain area, we have this density drop. Let's say here from 1 to 0.1, which represents our coronal hole. And we also have this wave for plasma flow velocity and vertical magnetic field in that direction. These are just function of the density. Let's see what's happening. So let's focus on the density. As I said, we have this certain fixed initial amplitude and this density drop, which represents the coronal hole. The question is, what do we expect now when this wave is approaching the coronal hole? What would we see? The left side or the right side of the coronal hole. So let's go, and in the course of this talk, I will show you that we will see first reflection and transmission, which anyway supports the wave theory. What is even more important, there will be stationary features at the corner hole boundary. Why is this so important? Because these stationary features were one of the main reasons for the development of the pseudo-wave theory. And I will show you that these stationary features can also be built up by the interaction of an MHD wave with the coronal hole. We will also see the formation of a density depletion, and I will show you the influence of the coronal hole density on these different effects like reflection or transmission. So, go to the first movie. Beginning a little bit fast. So the wave is steepening, forming a shock front, entering the coronal hole with low amplitude now. Leaving the coronal hole again, we see this transmitted wave, we see this density depletion, also reflection here and here. So definitely here what we see is the transmission and the reflection and the density depletion. In the next movie, which will be a little bit slower, let's focus on this part, on the left coronal hole boundary, okay? So, again, the wave is moving towards the coronal hole boundary, steepening, forming a shock front. And now it's entering the coronal hole. Amplitude decreases. And what we see here now is a first stationary feature. It does not last very long, but it's definitely a stationary feature. And after some time, well, yes, now a second stationary feature occurs. This is just caused by the interaction of this MHD wave with the coronal hole. Well, what we now have is a certain initial amplitude, and we had a fixed coronal hole density. What we can do now is we can take different coronal hole densities, also to cover, let's say, the observational range, or compare our results then afterwards with the observations. So what we can do, we can take also different coronal hole densities, let's say not only a drop from 1 to 0.1, but a drop, for example, from 1 to 0.2, 0.3, 0.4, or 0.5. And then we can compare the influence of the coronal hole density on the different effects. We can also do the following thing. We could take different initial amplitudes, let's make it a little smaller or larger like this. But first, let's look at the comparison for different coronal hole densities. Again, the wave is approaching the coronal hole, and we already see different things are going on. Some waves are faster, the density depletion is stronger in a few cases. So once again, a little bit slower. Okay. So wave is steepening, forming a shock front, entering the coronal hole, and let's stop it here now. What we can see already here is that for sure in the case of a small coronal hole density, due to high alpha and speed, the wave goes through the coronal hole much faster, and the amplitude is very low compared to the case where we have a larger coronal hole density, let's say. And what we also can see here for this first stationary feature is that the smaller the coronal hole density, the smaller the peak value for the first stationary feature. What we can see now for the transmitted waves is that the smaller the coronal hole density, the initial coronal hole density, the smaller the amplitude for the transmitted wave, and on the other hand, the stronger in that sense the density depletion. What we actually did with in our simulations is we did simultaneously runs for different initial amplitudes or different coronal hole densities. And what I showed you before is just different cuts through this figure. So when we look at our simulations we actually performed with different initial amplitudes, that's the case here, then we will see when I will run this movie that it's clear for the large amplitude waves, they will arrive much earlier at the coronal hole, and we also have different effects at the coronal hole boundaries and inside the coronal hole. Okay, so that's the actual simulations. And we see the density depletion, transmit waves, stationary features, and so on. And also, I mean, there are a few more effects, like reflections inside the coronal hole, but I don't want to go into these details at the moment. So just to make it very clear what we did. So the lower panel here is again the actual simulations we performed. So simultaneously taking here different coronal hole depths. And in the upper panel, it's just, let's say, 5 different cuts through the figure in the lower panel. And when we let it dry, it looks like this. And again, we see the different effects for different coronal hole densities. First stationary feature, second stationary feature, reflection, density depletion, and transmitted wave. We could also zoom in detail now in the range of all these different effects. Let's say, for example, this is really inside the coronal hole. And again, we see that in the case of small coronal hole density, the wave is going through the coronal hole much faster, but the amplitude is very low. We could also look in detail the first stationary feature. As I said, this blue one is the case for a very small coronal hole density, and we see that the peak value of this first stationary feature is the smallest one, whereas the peak value for the case of large coronal hole density is the largest one. In contrary to the second stationary feature, which is actually interesting, because as I said, the smaller the coronal hole density, the smaller the peak value for the first stationary feature. But the smaller the coronal hole density, the larger the peak value for the second stationary feature. And what we did now in detail, paper which is just in review, is really doing a kinematic analysis for all the different features, for transmitted waves, stationary features, for density, plasma flow velocity, position of the amplitude, phase speed, and also magnetic field in vertical direction. So I will skip maybe the... So we did this analysis for all the different features. You can also see, like I said, for the second stationary feature, we see in the case of low coronal hole density, it occurs first, but the amplitude is the largest one. As I said, let's skip this. It's at the moment a very simplified simulation and a simplified initial setup. So in the future, we would like to go to a more realistic simulation setup, let's say, especially concerning the shape of the coronal hole, really to take into account a circular or rectangular shaped coronal hole, maybe you can see then a refraction or something like this, also include gravity. At the moment, it's not performed in 3D. Well, the 3D code is already existing, but not used for this case. It's also planned to do a detailed energy analysis, so that we really can check how much kinematic, how much magnetic energy is coming into the coronal hole, how much is leaving it. And what is definitely interesting is to take different lengths or widths for the coronal hole, especially to compare to the observational cases, so that we can see at which length of the coronal hole really the wave is dying out, so that it cannot leave the coronal hole then anymore. This is also worth a study, and so just final conclusions. So I was talking about the interaction of large-scale amplitude waves with low density area, like a coronal hole, and we saw different things. First, we saw secondary waves, like transmission and reflection, which anyway supports the wave theory, because only waves can fulfill or can guarantee such effects. Second point, which is very important for us, is that we can see that the interaction of these waves with the coronal holes created stationary features. And as I said, these stationary features were one of the reasons for the development of the pseudo-wave theory, but we could show that also the interaction of the wave with the coronal hole can lead to these stationary features. Third, we saw the formation of a density depletion, which can be interpreted in the observations as coronal dimming, so it also kind of this shows good agreement. And last thing is, we showed how big the influence, how important is the influence of the coronal hole density to all the different, okay, I see the skull blinking, yeah, to all these different effects. So, but that's it, thank you.
I would like to talk about two fluid numerical simulations of solar speakers. Our main goal is to develop even more realistic model of solar speakers and to investigate how ions and neutrals evolve in these speakers. Here we can see some basic properties of solar speakers. There are nice indicators if our simulations show real speakers, so there are some another types of solar jets. These properties may vary depend on observations, but these are just some basic stuff. In our model, in our code, that is Joanna code that was previously announced, we use this set of two fluids equations. Basically saying we have equations that describe two fluids. One fluid is ions. What is the most important part of this is that ions depends on magnetic fields. They interact with magnetic fields. And the second fluid is fluid that describes neutrals. And as we know, neutrals do not interact directly with magnetic field. But neutrals interact with magnetic field in other ways because they interact with ions. Yes, here we have some collisions between ions and neutrals for recombination and for ionization. And why is the two-fluid model so important in modeling solar speakers? Basically because speakers evolve on the edge between two worlds. Yes, below transition region we have very low ionization. We have there many neutrals, but when we cross transition region going higher up, the plasma becomes mostly fully ionized. Yes, and the second big difference between these two regions is that below transition region we have high density. So we have there many collisions between these two fluids, so they are strongly coupled. But when we go up in corona, these two fluids are no longer such coupled in such a way. Here we have magnetic field that we are using. It was described by Law in 1985. On the right side we have this magnetic field in Cartesian geometry. On the left side we have equations for cylindrical geometry, but we have also this in 3D and in other models, depends on what we are now investigating. And here is plasma beta that results from this magnetic field. And plasma beta describes basically which part is more important, if it is gas pressure or it is magnetic pressure. And as you can see, if we excite speakers somewhere below the transition region, most of the region where the speaker will evolve is dominated by magnetic pressure. How we excite these speakers? We decide to use some time-dependent pressure perturbation in both of these gases, in ions and in neutrons. We dig up some observation of other jets, not exactly spicules, with similar, where similar energy release at their base was observed. So we decided that it is better to use this kind of time-dependent pressure perturbation that will evolve in time than use just simple pulse, because pulse that will just one pulse is not exactly what is physically correct. And we finally have some numerical results of our simulations. On the left side we have ions, and on the right side we have neutrals. And here we already can see many differences between dynamics of these two fluids. As we can see, the spicule in ions is as we can see, spicule in ions is okay. Let's stick to this. Spicule in ions is very thin. It is rarefied because after the first slow shock, there comes contact wave, and after this we can see rarefaction wave, and it results with quite rarefied spicule. What we also can see here is that above the apex of the spicule, we can see a stream of ions that are injected higher up into solar atmosphere. This is something that we do not see in neutrons. Yes, above the neutron spicule, we do not see this stream of particles. What we can see on the first, what is also interesting on the first panel, is that slow shock. That you see this round structure, yes? That this signal in coronal plasma, in neutrals, is going almost isotropically. Why is so? Because in corona these two fluids are not strongly coupled. So ions follow magnetic field lines, yes? But neutrals here do not follow magnetic field lines, and they are only slightly pushed by ions because there are only very few collisions between ions and neutrals. Also, the spicule in neutrals is wider, as you can see from spicule in ions. Once again, here ions and here neutrals. It is also because of the same reason. It is wider because the magnetic field do not hold it along magnetic field lines. And also we can see many instabilities in this fluid. In ions, these instabilities cannot evolve because they are suppressed by magnetic field. Okay, and here we can see the temporal evolution of density. Top left is density of ions, bottom right is density of neutrals, top right is velocities of ions, and top and bottom right is velocities of neutrons. As we can see here, spicule in ions is generally, it has almost the same height, but it is generally rarefied inside. The rarefaction wave is clearly seen. This rarefaction wave is not that seen in neutrals, but trust me, there is this wave. If we will check, there is such a wave. But what is important on the velocities panels, we can see that if we combine two top panels, we can see that this part of ions that do not fall back to the transition region is going higher up, and we trace them to the 50 megameters, and they are even accelerating. while the neutrals, mostly all the neutrals come back down to the transition region. As you can see, this is a typical temporal evolution of solar spicule type 1, type first. Yes. So, going fast summary, as we see, the ions and the neutrals evolved almost the same way, but there are differences that we expected. These differences comes mostly from the fact that ions interact with magnetic field directly, while neutrals do not. This. We also revealed that neutral acoustic gravity waves propagate quasi-isotropically in solar corona, while they do not this in chromosphere because strongly coupled, because these two fluids are strongly coupled. The core of this spicule consists mostly of neutrals, as this is chromospheric plasma, but they are and the temperatures of this spicule is higher than typical chromospheric plasma. Their temperature is close to transition region temperatures, and as we saw, the substantial part of ions is injected higher above the apex of the solar spicule, following these magnetic lines higher up. So just after summary, just maybe one part, here are some of our first comparisons between our numerical results and between some observations. Observations are dashed line, and our results are this bold line. These are profiles of temperature and observations, so they match quite good. So I think that's it.
Ladies and gentlemen, let me draw your attention to our current ongoing study about spectral inversion of the H-alpha and infrared calcium lines 8542, based on observations taken by the SSD CRISP instrument in chromospheric jets. Within this beautiful workshop, we could witness that chromosphere is widespread and densely populated with different kind of jets, displaying a very broad range of expansion velocities. Among them, in the past years, very intense increase gained so-called type 2 spicules, displaying very vigorous dynamics and really enigmatic behavior, and it attracted lots of research, leading to progress in our understanding of chromospheric structures and understanding between the lower chromospheric layers and the upper chromospheric layers. Just to mention that the speeds which occur in these type of spicules reach the values about 50–100 kilometers per second, and these highly dynamic jets trigger one quite natural question. They occur within some ambient medium, and the interface between two medium may, let's say, trigger kind of instabilities which are named as Kelvin-Helmholtz instabilities, and they are potentially considered as a process converting the turbulent energy from the interfaces of these flows to heating. My colleague Timothy made estimates of energy budget delivered through different mechanisms like thermal conduction, Joule heating, viscosity, and ion-neutral collisions necessary for converting energy of this process to real heat of the corona. And as you see, there are very, very long. In contrast, there is a real potential of Kelvin-Helmholtz instabilities to convert this turbulent energy into the heat much, much faster. And therefore, this idea deserves much closer attention in our future. Just to show you what am I speaking about, let me play this animation showing that type specules occurring in the calcium H passband in the silk instrument are accompanied almost simultaneously with their counterparts seen in the iris passband. So there is clear evidence of the conversion of the energy into the higher temperatures. And here is a kind of a didactic animation showing evolution of these Kelvin-Helmholtz instabilities supposed to occur somewhere at the outer boundaries of these jets. So our aim with this study is to try to look for these instabilities and to provide at least the ground for a broader survey of these phenomena. So to identify, first let me show you aims of this study. First, we need high quality material for identification of large statistical sample of chromospheric jets. Of course, the best choice or the best tool for this is the Swedish Solar Telescope. And at this stage of the study, we decided to interpret data obtained by the CRISP instrument with a kind of modified cloud model, which interprets the observations in terms of the source function, the line center optical thickness, the Doppler width, and the line of sight velocities. All these quantities are necessary for, let's say, convincing judgment whether we see in the jets presence of some non-thermal broadening, which is supposed to be a manifestation of Kelvin-Helmholtz instabilities. So we organized a coordinating IRIS SSP campaign, which was performed in the name of the previous year. It was generously supported through the SolarNet campaign. I would say that without this support, these observations wouldn't happen. And we observed almost simultaneously H alpha and infrared calcium 8542 in the range plus minus 1.4 angstrom with 15 points within the scanned frequency or wavelength interval, and calcium 1 was scanned in the interval plus minus 1.2 angstrom with spectral scanning of 1.1 angstrom. Resulting temporal cadence of this data set was about 12 seconds, and the data reduction was performed by a loop van der Voort in the also. Let me show you an example of the data used within this study, where I selected for the purpose the animation coming from the line center of the H alpha, and in the blue wing, which is about 1 angstrom off the line center. And on the right, you see the line center movie showing the scene in the core of infrared calcium 8542, and for complementarity, on the right you see the same white sun solar chromosphere as is shown in the blue wing of infrared calcium line. Apparently, both these blue wings show many jet-like structures shooting out from these network elements, and they immediately attract attention and a potential, let's say, manifestation of type 2 specules and good candidates for looking for Kelvin-Helmholtz instabilities. And for interpretation of this data, we adopted a modification of the classical Becker's cloud model. Just for your recollection, this classical cloud model was introduced in 1964 by Jacques Beckers, and in the time he evolved sometimes because people realized that the cloud model is quite sensitive on the background intensity. So very quickly, what you see on the left is our observable, which is the intensity within line profile, and on the right is multiplication of the background profiles, and the observed intensity is represented through the constant source function and optical thickness, which can be represented through line center optical thickness multiplied by absorption profile, which is dependent on the line width and the line of sight velocity. So this quite simple model interprets the observed intensity by 4 free parameters: source function, line center optical thickness, line width, and Doppler velocities. To remove the strong dependency of the classical cloud model on the background intensity, Liu and Ding suggested a kind of the modified cloud model, which appeared to be very useful for interpretation of highly asymmetric profiles, which do occur within chromospheric jets. Many studies previously, like Rope van der Voort, showed that like a fringe of HRD events is highly asymmetric with alpha profile. So naturally, our attention led to choosing this modified cloud model for interpreting our observations. It's on the left side is simple observation or observable, which is simple difference of symmetric intensities on both sides of the profile, and it can be interpreted again with these 4 parameters. So just applying Lavender-Marquardt risk and minimization methods, which was triggered by comparing the observations by pre-calculating database of the guess parameters, we interpreted our SST observations in these terms of free quantities. Nevertheless, I have to point one thing. We needed to introduce asymmetry of the background radiation, otherwise this model didn't work quite well. So we applied this model on such, let's say, carefully selected samples of chromospheric jets like this one. You can see its evolution in H-alpha in blue wings on these movies, of course, because time difference between these observations are just a couple of seconds. We can consider them as mostly simultaneously. Transfer motion of this feature is quite obvious. Here is an example of observations or observed asymmetry of one particular profile taken out from this jet. It's fit obtained by the modified Klein model and adopted asymmetry of the background profile. At this stage, the results is quite optimistic, but because we have these 4 parameters, we can translate these 4 parameters also in synthetic profiles. In that case, the modified Klein model has some problems, because when we don't have any asymmetry, like in the far wings or line center, it fails to reproduce very well the observations. So this is a real problem. But anyhow, what you can see here is the structure of the chromospheric jets that we see in NH-alpha. So here is the source function. A closer look on this structure shows that the source function decreases outwards from the jets towards corners. At the same time, the optical thickness decreases outward from the line core, which is more or less consistent with basic intuition. We see more or less coherent motion of the whole structure with the apparent Doppler velocity of about minus 30 kilometers per second, and there is no clear structure in the Doppler width. Here you see simultaneous, let's say, maps of the structures obtained by the inversion of the chromospheric line. And here is the situation a little bit interesting, because again we see the increase of the source function outward from the line core and simultaneous decrease of the optical thickness outward. But look at these features. In the case of the Doppler velocity, we found clear signature of fast downward Doppler velocity at the boundary. Maybe we could think that we observe a big direction of flow occurring within this structure. At the same time, we see slightly increased Doppler width occurring at the same place. Now, a very quick statistical overview of all these results. In the case of the source function, we see clearly peaking distribution of the source function at the point of about 0.23, but the source function of the calcium line shows more or less flat distribution. In the case of line center optical thickness, the typical values are about 0.7, 0.82, and I think this is quite critical point for our research. Can we consider these values as representative for optical thin? If yes, then we can translate our observations also into the non-thermal broadening. If not, I'm not sure how to interpret it into the future. Doppler width. We found significantly smaller Doppler width in the calcium infrared line, which shows double peak distributions, suggesting light cold plasma occurring within this feature. In the case of the H-alpha structure, the Doppler width are significantly larger. And here is the statistical view of our results obtained from the line of sight velocity. Apparently, the line of sight velocity is much larger in the H-alpha observations of this jet. And we see this kind of bifurcation of Doppler velocity occurring within the jet observed in the infrared calcium line. Again, it's a quite interesting feature, but we need to check these results more carefully to be sure that we really see signatures of possible bidirectional flow occurring with this structure. So, because I'm approaching to the end of my time, here is a very quick summary what we did within this study. We applied a new version of the modified prime model, originally developed by Liu and Link, and this method was applied to infer parameters of the chromospheric jets in the H-alpha and calcium lines. We found clear increase of the source function in both H-alpha and calcium outward from the core of the jet. We found clear decrease of the optical thickness from the core of the jets outward. The distributions of the Doppler width are not simple, but in the case of the calcium, we see double peak distribution, suggesting the presence of light cold plasma. And large Doppler velocities were found in the case of the H-alpha than in the calcium. And we see some possible signatures of bidirectional flows. At the end, I cannot miss the chance to thanks again to everybody who was working very hard on the SolarNet project, and personal thanks should go to Robert van der Voort, who helped us with this reduction. Thank you very much.